Hello class, this is lecture 5B, Properties of Colloids. Today we're going to focus on describing the cause and ramifications of a couple of different properties of soil colloids, including shrink-swell properties, permanent charge, and pH-dependent charge. So there are clays that are shrink-swell clays, and we discussed this to some extent in lecture 5A. So this happens when we have 2-to-1 expanding clays, and they kind of look wavy like you see here in the top right. And what happens is water is attracted to both the charges on these clays, but also all the cations that are absorbed onto these charge sites. And so water is attracted to these clays and it forces its way in between the layers, and those layers kind of spread apart. And as they spread apart, those clays expand. And so as they expand, that really kind of scales up. So at a large scale, you can have a ped that can increase in size quite a bit. But at the profile scale, it's big enough that it can crack basement walls or damage roadways or things like that. So it is a concern from an engineering standpoint. So on a house, it can cause some issues with windows and doors that aren't aligned. It can have a foundation that moves or heaves, and it can get issues with cracked foundations or even cracked walls and cracked pipes. And when we build houses on these soils, so if you remember back to learning how to use the web soil survey, there are soil mapping units that are rated as very limited for building houses with basements. And it doesn't mean that, and one of the limitations can be that those soils have high shrink-swell properties. It doesn't mean that we can't build a house there. It means that we have to engineer our house around the limitations of those soils. So it just costs extra money to take the extra steps to solve this. So some of the issues, or some of the ways we can solve it, is we can dig footings that extend deeper into the soil to a depth where there are no shrink-swell problems. So footings is one method. We can also irrigate the foundation so that that soil never has a chance to dry. And so if the house is built when the soil is expanded and it stays, and the soil around it keeps wet at all times and it keeps expanded, then that's one way to solve it. And a third way is to try to drain the foundation to keep it dry at all times. So in Manhattan, we have a lot of houses that are built on soils that are problem soils when it comes to shrink-swell. And the approach that is used in Manhattan is all houses built from 1978 and onward and later, those houses have to have a drainage system around the foundation and drainage going underneath the slab if it's a slab house or a slab basement. And that drainage keeps those soils dry so they never actually get wet enough to expand to the extent that they'll crack a wall. Houses that were built prior to 1978, depending on what exact soil they were built on, tend to have issues with basements. Now, one kind of interesting story about these shrink-swell properties of soils is what we call the Research Triangle Park. So I went to graduate school at North Carolina State, and here's a map showing NC State, which is in the city of Raleigh. So you can see, let me get my pointer here. So you can see, it says North Carolina State University, and it's right there in the middle of Raleigh. And then Duke is in the city of Durham, and UNC is in the city of Chapel Hill. And so we have these three schools that are on, if you're a basketball fan, you've probably heard the term Tobacco Road. So Tobacco Road is mostly North Carolina schools that are in the middle of tobacco country, and they all have a pretty storied basketball history. But they're all large R1 research universities. And so there is a lot of expertise when it comes to these universities. And this expertise allows for a nice recruiting bed if you are a say, a biotech company or an engineering firm or something like that. And so what ended up happening with this area is that there's a geologic part of North Carolina that goes kind of in a diagonal stripe from about the southwest part of the state to the northeast. So it kind of goes in a line like this, and it's called the Triassic Basin. And the Triassic Basin was a split in the continent, in the North American continent, whereas the North American plate started moving westward. Part of it was moving faster than, the western part was moving faster than the eastern part. And so as that happened, it created a rift. So if you ever heard the giant rift valley in Africa, it's the same concept. So we have this rift, and so they call it the Triassic Basin because it occurred during the Triassic period. And what ended up happening is we had a lot of mud and water and stuff that got stuck in this low-lying area, and it created perfect conditions to create 2-to-1 shrink swell clays. And also these clays, just given the total history of the site, they're also high in aluminum. And so from an aluminum standpoint, they're very difficult to farm if you're actually trying to grow a crop. And they're difficult to build a house on because they're shrink swell. And so they can't be developed for real estate easily or cheaply, and you can't farm them. And so it was sort of a barren area with no real use of the land prior to developing the Research Triangle Park. And what they ended up doing is they created this Research Triangle Park in the middle of these kind of problem soils. And what they did is they marketed this area as an excellent place to be able to recruit from these 3 large universities. If you are a company like, say, Bayer, or some pharmaceutical companies, or some biotech companies. So Monsanto used to have a research facility there, Bayer Crop Science. And also companies like Caterpillar and John Deere have engineering facilities there. So there's a lot of companies that hire students that are coming out of UNC, Duke, and NC State, and so they're able to hire them out of college, and they can stay close to their old college stomping grounds, and they build these large facilities in these problem soils that are shrink swell soils, but they engineer around that for actually building those facilities. So most of them did one of those options like I showed in the previous slide. Most of them irrigate their foundations so that there's no shrink swell that occurs. But it's kind of an interesting application of regional development to develop around the problems associated with. Now, shrink swell soils are problemsome when it comes to building structures, but it is useful in other scenarios. So for wells, for example, when we install wells, usually we have to cap the well in some way, and just to fill the hole that's created when we actually dig the hole for a well. And so for monitoring wells, which are used in soil science pretty frequently, we might be trying to figure out what the water table depth is, or we might be trying to figure out if water is rising from an area or going downward using piezometers, or we might have a monitoring well like you might see at a gas station to make sure that there's no gasoline that's leaking out of the underground storage tank. But in all these scenarios, we have a well that looks about like you see on this picture here. And once that well is installed, then at some point we will add a bentonite plug. And bentonite is a type of a 2-to-1 expanding shrink swell clay. And so we have this area that's actually open up to the water table with all the slits cut in the pipe down at the bottom. And then right above that, we have the bentonite plug, which prevents water from above ground actually flowing down what was disturbed during the installation of that well. And so as that clay expands, it plugs that hole and makes it impermeable to water from above. And then we put a little dome on top so that water sheds away. So there's kind of a grade to move water away. And this dome, or this little mound here, is usually a mix of the soil that was dug out of the hole and some bentonite. So they have some shrink swell properties as well. So this is done in drinking water wells. Those are much deeper wells, but the same process applies. So we don't want stuff that, say, fertilizer or herbicide sprayed on a lawn to wash into the hole for our drinking water well, because that would potentially infect our drinking water. So it keeps drinking water clean, and it ensures the water quality or water level data that we're trying to collect from a monitoring well is actually good. Another application for these shrink swell clays comes from Unit 1. So you guys learned about one of the 12 soil orders, Vertisols. In the case of Vertisols, these are soils that are dominated by shrink swell 2-to-1 clays. So we need a clay content that's 50% or higher from the surface down to a depth of at least 50 centimeters. And that's how we'd actually describe a vertisol. And these vertisols, because they have so many shrink swell clays, when they dry out, they usually have these large cracks here. And these cracks are big enough to lose a cell phone. Now, I didn't take this picture, but this is what we call a flip phone, for those of you who have never seen one of those before. But this flip phone just kind of shows you the scale of what these cracks look like. And so that would be during a dry period. During a wet period, it would look like this picture down here, where we have lots of puddles. So as those soils swell, those cracks close in, and the soil continues to kind of tighten up, and eventually there's no infiltration that can take place because there's almost no macropores to speak of in the soil. It's all just kind of fills up either with water or just fills up from the expansion of these clays. And some exhibits or sure signs of a vertisol, we usually get sort of a wedge structure that occurs. So going back to our structure that you learned about in Unit 2, we can get slick sides and wedge structure for the soil structure in these vertisols, as well as these deep cracks. And these occur where we have kind of certain types of conditions, but you can see that they occur throughout the United States. So lots of them down in Texas. We got quite a few in Oklahoma and Kansas. There's quite a few in South Dakota, Montana, North Dakota, California, and Oregon, and also along close to the mouth of the Mississippi, in the Mississippi River Basin there, and in the Black Belt in Mississippi and Alabama. And these form generally where we have conditions with lots of base cations. So if we have lots of base cations and the right type of moisture conditions, we can get these vertisols that form. All right, so I have a video that I want you to click on the link here to actually go and see. But this is, if I was teaching you in person with this lecture, I would have showed you a very similar demonstration. But this is Dr. Graville. He is a soil scientist at Purdue and a friend of mine. And it walks you through what the models of clay look like with these ball and stick models. And he has a couple different demonstrations. One where he has soil connected to a battery, and one of the wires that's in this little soil slurry, the soil will actually stick to the wire based on charge. So I want you to watch the video to figure out how that works. And then he also filters some different juices through some columns of soil, and it will actually change the color of the juice based on the charge that comes from the soil and comes from the food coloring itself. So go ahead and watch that video. And now I have a discussion question for you. So this is a graded discussion question, and there are 3 parts. So first part is soil colloids primarily have a what charge, either positive or negative. So I want you to answer that, and then I want you to describe a simple experiment that you could do to demonstrate that. So again, if you watch the video referenced in the previous slide, then you can describe a simple experiment. And I also want you to give some examples of the sources of those charges, which I'm going to show you right now. So one example, or one type of charge, or one source of charge, is isomorphic substitution. And isomorphic substitution is where we have a cation. In this case, in the octahedral layer in a clay, we have a cation like magnesium or iron that has a 2 plus charge that takes the place of aluminum in the octahedral layer, and aluminum has a 3 plus charge. So we're taking a 2 plus cation and replacing a 3 plus cation with it. So what would have been balanced had there been aluminum present is now imbalanced with iron or magnesium. And as a result, we end up with a net negative charge because not all of the charges from the water, or from the oxygen are balanced. So we end up with a negative charge there. And this is a permanent charge that's built into the crystal lattice of the clay. It does not change based on pH. This is a permanent charge. And isomorphic substitution is due to the size of these cations. So silicon in the tetrahedral sheets, silicon is one of the smallest cations that are in the soil, and it has a radius of 0.042. And aluminum and iron 3 plus are similar in size, so they can take the place of silicon. But when that happens, because there's less charge, we end up with a permanent charge. And in the case of octahedral sheets, we can have aluminum or iron at the center, and iron 3 plus. And if that's the case, then there's no permanent charge. But if we have magnesium 2 plus, zinc 2 plus, or iron 2 plus, then in those situations, we actually get a permanent charge that's built into the octahedral sheet. And if we look at the chemical formulas for minerals, if there's no substitution, you would see in the case of kaolinite, we have aluminum present, but when there is some substitution that occurs, you would see both aluminum and magnesium described here. Or another example, for montmorillonite, we can have substitution in both the octahedral and tetrahedral layers. So instead of Al2 for the octahedral, we have aluminum and magnesium. And instead of silicon, we have both silicon and aluminum. So this tells us that there's magnesium substituting for aluminum in montmorillonite, and there's aluminum substituting for silicon in the tetrahedral layer. So that was isomorphic substitution. Now, another source of charge that is pH dependent occurs at the broken edges of colloids. And what you're seeing in this figure is we have kaolinite, so a 1-to-1 clay. So here we have our tetrahedral layer in the bottom, octahedral layer in the top, and then we have the very edge of a clay mineral where it's been broken off. And what we're seeing here is depending on the charge, or depending on the pH, we actually get a difference in charge. So let's start with pH 7. So at a neutral pH, at the edges, we have some oxygens that don't have all their charges offset by another silicon, or another aluminum, or another silicon here. And so at the very edge, we get charge that occurs in this kaolinite. And we end up with a -3 charge. And that's at pH 7. If we look at pH 5.5, then we end up with a -1 charge. So what's happening is we have a more acidic solution, and the more acid, or the more hydrogens we have floating around in solution at a lower pH, then we actually have more hydrogens, and those hydrogens are more apt to find a negative charge site and just attach themselves there. And so what we call protonate those negative charges, and that eliminates that negative charge from actually being able to absorb other cations. And as we lower the pH even further, we have even more hydrogens floating around in solution. So much so that all of the negative charge sites have been filled up with all these excess hydrogens that are floating around in solution. And we actually get more cations, or more hydrogens that are attaching themselves to the clay than normal, and we end up overcompensating for all the negative charges, and we end up with a net positive site. So in this case, we can actually get anion exchange capacity, where the colloids, once they have all the hydrogens attached, actually have a positive charge, and could then potentially absorb some anions. So this is a pH-dependent charge, and it occurs at the edges of clays where they've been broken off, and all the charges aren't balanced well. So it's pH dependent. And the way to think about this is at a low pH, we have more hydrogen in solution. So going back to chemistry, if we look at the concentration of hydrogen, if we have a pH 4, that means that the molarity of hydrogen in solution is 10 to the negative fourth, or in other words, 0.0004, or excuse me, 0.0001. So 10 to the negative fourth moles of hydrogen per liter. If we had a pH of 7, then the concentration of hydrogen is 10 to the negative seventh, or 0.000001. So the difference between pH 4 and pH 7 in terms of the concentration of hydrogen is 3 orders of magnitude. And what I mean by that is there's basically a 1,000 times more hydrogen floating around in solution at pH 4 than there is at pH 7. And the end result of that is at pH 4, most of these negative charges are protonated, whereas pH 7, most of them are deprotonated, meaning that there's an available negative charge that could absorb a calcium or magnesium or some other cation. Now there are other pH-dependent charges, and one of those comes from organic compounds. So at a low pH, where there's a lot more hydrogen in solution, these functional groups, so carboxylic, phenolic, and alcoholic groups, these all are protonated and there's no charge. So that negative charge has been filled up with a hydrogen. And as we lime the soil and raise the pH, then those charges become available because these alcoholic groups and phenolic groups and carboxylic groups, they deprotonate, meaning they lose their hydrogen, and what's left behind is these oxygens with an extra negative charge waiting for the next cation to come along. So on the right side is what it would look like at a high pH, or high is in neutral, and then on the left side it's what it would look like under a low pH, so say pH 4 or 5. So we get more charge with pH-dependent charge with more neutral to alkaline pHs. And as we get more acidic, we lose charge because there's so many hydrogens floating around that it fills those charge sites with hydrogen. And these exchangeable cations, they do occur at the edges of clays. So I made this point in lecture 5A. Most of these exchange sites occur, if you're looking at a stack of clays, they're going to be at the edges or on the front and back cover of the book with all these pages of clays, all these clay crystals all kind of stacked on top of each other. So most of the exchange sites happen on the edges and the top and bottom of each clay domain. And one more point for how these charges interact with cations. There's a couple different ways that this can occur. So we can have what we call an outer sphere complex, where a calcium, as an example, is surrounded by all these water molecules, and the attraction between the negatively charged oxygen on the clay passes through water to get to the calcium. So there's an attraction with a water molecule in the way. And so this would be what we call an outer sphere complex absorption of this cation. And then we have inner sphere complexes where, say, something like a phosphate will actually share the oxygen with the clay itself. So that's an inner sphere complex. So this is a much stronger bond. So this is a covalent bond as opposed to an ionic bond. So inner-sphere complexes are covalent bonds where they're sharing elements. Outer-sphere complexes where they're sharing, or they're attracted just due to charge. And then we have diffuse cations that are floating around in solution. And there's a video that's called Sorption that you need to watch too. So make sure you find that within Canvas. And that will wrap up the Colloid Properties lecture.